decide where to place the card. 26% have how many years of experience? The next line is over here. $1. Mark, this is what you label. This piece of the pie is only 15% of the pie, and it was 10 to 14 years of experience. This is what you mark. Mark is 75%, but you label 14. This piece of the pie is 14%, and it was 15 to 19. 88, 85, 85, 88, 13%, and 13% are 20 to 24. 98 is 10%, 25 to 29. Now, when you don't have room to write inside that time, you draw a little arrow down here and say 2%, 2% from 30 to 34. You don't have room to write in the time, you just draw a little arrow and label that piece that way. Now, again, this doesn't tell me anything unless I put a time along here that tells me that this is years of teaching experience. I need to know a little bit more. I need to know that this was 80 college professors. And again, if I knew the college, if I knew the year, any other information I wanted would go here too. This time my time has a little bit more because the time also tells me that this is years of teaching experience and this for college professors. Half the numbers are smaller than this amount, half X bar, U is the mean of a population. And you remember when we talked about this earlier, a population is every member of the group to be studied, but a sample is just a small part of that group. We have a sample, we call it X bar, and we have a population, we call it U. Now, the formula for finding this is the same. So you get the same number whether you label it X bar or U. There are going to be late formulas we see later on where it makes a difference. The sample uses a different formula than the population. So we're going to have to be very careful about how we label them so we know what we're doing with the sample and the population. So when you're going to find the average of the numbers, the first thing you have to decide is it a sample or is it a population? So you know how to label it. A sample would say if we took a sample of students at Southwest College. A population would be anytime they say all or everybody. This is all of the employees in a small company. They say all or everybody in the population. They say this is a sample or this is part of the group. Now, like I said, you already know how to find the mean. The mean is what you call the average reward. You add up all the values and you divide by the number of numbers that you have. We are going to use a formula for the mean. Even though you already know how to do it, when we look at these formulas, get used to how we write formulas in statistics. The mean, we say, is this symbol right here, which is the summation symbol. The sum of all of the x's divided by n. And that's what you've always done. You add up all the values divided by how many numbers you have. What we need to get used to is this symbol right here. It's the Greek letter of sigma. It's the capital sigma. Greek letters have small letters and large letters just like we did in our language. This is the capital letter sigma, and it's called a summation sign. Whenever you see that in statistics or any other formula, that's going to add up all the values. Right here, this is the x's, and this is how we label our listed numbers. It said add up all the numbers and divide by n, and you have to know that n stands for the number of values. Now, I say you find the mean the same whether it is a sample or population. The only difference here we would call we add up all the values, but we would call it a capital letter n. Small n says we have part of the numbers as a sample. Capital N says this is all the numbers there are. This is the population. So again, it's just the way we label things. We get the same number whether we labeled it X bar or U. The label is going to tell us whether we're working with a sample or a population. Like I said, you already know how to find the n. We're just introducing a notation here. We'll see it as a little to find the median, we said the median is the middle number. If we have an odd number of values, there will be one number there in the middle. You might have a list of numbers. Odd value. There's an odd number, and this number right here in the middle is called the median. numbers are smaller than 5.5, positive numbers are larger than 5.5. So it's either the one number in the middle, or it's the average of the two numbers in the middle. So the last measure is the mode. It's an abbreviated mode, abbreviated MO. It's the number that appears the most often. Well, you can see from these two examples that there's not always a number that appears any more than the others. These two examples that I just wrote here do not have a number that appears more often. So in these two examples, there is no mode. That's the trouble with the mode. There's not always a mode for every set of data. There's not any number that appears more often than the others. The other problem with the mode is there may be more than one mode. Here the numbers 3 and the number 6 appear more than the others. Spread data has two nodes, 3 and 6. So of those, there may not be a mode. There may be one node, or there may be more than one node. Now, in this case over here, where there was not a number, make sure you said that there was no node. You didn't say the node was equal to 0. If you said the node was equal to 0, you're telling me the number 0 appears the most often, and there is no 0 in this list. So make sure you're saying no node and not 0. the numbers. So I say 595 and 39 cents. Now the value I hit is 54.090909. I can put the 09 is going to keep repeating. There's no real exact rule here for how many decimal places. It's more general rule of thumb. We usually say keep one more decimal place in the original values. These original numbers did not have a decimal place. Keep one more decimal place in the original numbers, and you would round this off. Normally that's what we were doing. But what was I talking about here? These were sample speeding tickets. What were these measured in? It was the cost of the speeding ticket. It wasn't how fast the person was going. This was the cost of the speeding ticket. And this was the cost. And it said the average cost was 54.1. Now that's the one exception to the rule about using one more decimal place if you're talking about money. Money always has two decimal places. So you can say $54.09. You're talking about money. You always keep two decimal places because you guys never say $54.1. You use 10 cents or 54.09. So normally you keep one more decimal place. This is money. Keep two decimal places. The average cost was 54.09. To find the median, before I try to find the median, those numbers have to be in order. And these are not in order. Here's a 70, here's a 40. You cannot pick out the median until these values have been put in order. So the first thing you should just have to take a few minutes, find it in order. There's a 25, 30, 35. Medians is just to look at those numbers and pick out one of them. After them are the medians, the number has to be in order. The values have to be in order. And since there are 11 values, there should be one number right near the middle. And if you look, there's 5 values above it and 5 values below it. So the median is 55. We already had the median. 5409, and now we have the also, when you put the order, it makes it much easier to see the node. What's the node? Is 78. If there's only one node, it's 78 here twice. Now, I mentioned before that in statistics, we don't just say X is equal to 54 and quit. In statistics, we're going to be interpreting every value that we get. And here we're going to interpret with a complete sentence. When you interpret data, I always want a complete sentence. We said that the mean is 54.09, so I'm just going to say the average cost of speeding tickets. out now on the salaries for all employees at Smith Corporation for 1995. And these salaries are $5,000, So look at this one as you consider what employees just make $5,000 when he was part-time. We had 5 employees that made $20,000 and 1 employee that made $250,000. Now I mentioned measurements, the superintendent, the means, or a way to summarize the data. Well, if you just had just two values, it would just be just as quick to look at the whole list of numbers and tell what was going on. We usually use these to summarize when you have like 200 or 300 numbers. These would make it a lot easier to understand. But I'm just picking a short sample here to look at so that you can see what's happening. First thing I'm going to do is find the mean, and what I call the mean XR or mu. I call it mu because I said all employees. I say all or everybody, you know, in the population as we call it. So to find that, the first thing I have to do is add up all the numbers. So the average here is 355,000 divided by the total number of values. We're talking about money, so I'm going to keep two decimal places. The average is $50,000, 714 and 29 cents. What is the median? Median right here is 20,000. And the mode. If I'm going to interpret this, I would say the average salary for all employees you think they are less, but if you look at that, there are some of them that are $20,000. So sometimes instead of saying half are less than $20,000, you say half the salaries are $20,000 or less. And I just think it's a slightly more accurate statement because half the salaries are $20,000 or less. If you were to go more, you would say half the salaries are $20,000 or more. That's a more exact statement to say they're this amount or less. $20,000 is the salary that appears the most often. Now, like I said, when you understand what this small set of numbers, it's just as easy to look at the set of numbers and tell what's going on. If you had 200 numbers, these three values would give you a good idea of what's going on. But if I just told you one value, if this was all I told you, it doesn't give you a good picture of what's happening very quickly. If I say the average salary is $50,000, you might think it sounds like something under work for me. But then if you look at it, say half the salaries are $20,000 or less, and most of the people there you'll see that, well, that's not that good deal. This number has been affected by one large value out there. One large value that makes its average quite a bit bigger than the rest of the numbers. And that's the problem with the average or the mean. The mean can be affected by a few very large numbers. And that makes this number not really representative of the whole group. It doesn't really represent the main group of people. So like I said, you told me the average salary is $20,000, you might think this would be a pretty good place to work. And if you look at these other pieces of data, you might realize that $50,000 is not really a typical salary. The average, because these others are so much lower, you know that there's only a few large numbers, and that most of the numbers are around $3,000. So that's giving all three numbers a better picture than any one value. But all of these, the mean and the modes, they all have advantages and they all have disadvantages. Comparison of the mean, median, and mode. First of all, the average or the mean. The mean is easily understood because most people have dealt with this and called it the average. The mean is easily understood. All you have to say is the average number is this, and most people have an idea of what you're talking about. They understand what you mean by the average. It's easily understood. It does use all the values. So that means everybody is represented in the group. If you're averaging your grade, every grade is represented in your average. It uses all the values. The main disadvantage of the mean is it can be affected by a few very small or very large values. It can be affected by just one or two real large numbers. And this example over here, one large number here makes the average quite a bit larger than the main group of the numbers. And it made this average where it doesn't really get a good representation of what's going on. And that's what it means by it can be affected by a few very small and very large numbers. If there was one number that's a lot smaller than the others, you have four test rates that are 90 and 1 0. That 1 0 can affect your average really bad. So it can be affected by a few small or a few large numbers. That's the main disadvantage of the mean. The median is easy to find and easy to understand. If I tell you half the people make $20,000 or less, that's easy to understand. So it's easy to find, it's easy to understand, but it does not use all the values. That can be a disadvantage up here, or it can be a disadvantage down here. It does not use all the values. Like here, the median is 20,000. It tells you what's going on in the cell, but it doesn't tell you if you have this one large number. If you did not have this one large value, it wouldn't make any difference to the median. So if you're just looking at the median, you don't know if there's one person down here that's making a whole lot more than the others. You don't even know about this one small one. not give you a complete picture. But usually if you use all three, you have a better idea of what's happening. The mode also has another disadvantage. The mode is not unique. The mean and the median are unique because there is one mean and one median for each set of data. Not unique since there does not have to be a mode and there might be more than one mode. So it's not unique. Mode doesn't always exist and there might be more than one. They're unique says there's always one and only one. But that's not true for mode. There may not be a mode, there may be more than one mode. So these are sort of the advantages of the mode. The great advantage of the mode is the mode is the only one of these three single genesis you can find for nominal data. Find the mode for nominal data. Remember, nominal data was any time you listed your data as a name or a word. If I went around here and listed how many males and females I had around, if I listed males and females, and if I said there were 17 males and 25 females, you can find the mode. The mode says that there were more females than there were males in this particular group. But you can't find the average. You can't average those numbers up. You can't find the median. So for nominal data, you can only find the mode. And the extra big advantage of the mode, you can find the mode for any set of data, even if it's known. Mention one more measure of central tendency. It's mentioned in the book. When you go to your homework, go ahead and define it as the mode and the big range. But I'm not going to ask for it. I'm just going to mention it because it's there. You see it in the book. It's on the previous. The big range. The big range is the highest number in your set plus the lowest number divided by 2. Very easy to find. You take the biggest number and the smallest number divided by 2. So we're not using big range much because it's not that easy to interpret and it doesn't really mean that much. Like I said, there's a formula. If I ask for it in the book, you can use it to big range. I will be asking for it in the test. When we talk about a set of numbers and we start comparing them, the numbers. All the numbers are around the center, but there's one really, really big number. The shape of the distribution tells us a little bit more about maybe the money. And look at the shape of the distribution. We're going to try to picture a frequency hologram. So we don't have the numbers here in a frequency distribution. We just had a list of 10 numbers or a list of 20 numbers. So we didn't have a frequency distribution. But if it were a frequency distribution, what would the shape be when I drew the frequency polygon? Now the frequency polygon is also the same shape if you were imagining the histogram. The frequency polygon and the histogram both had the same basic shape. And if you took anything, the histogram from the same set and you set it on top of the frequency polygon, the midpoint cell would be connected by the frequency polygon. If you had a frequency polygon and a histogram with the same graph, they would sit right here in the frequency cell in the middle of the bar. What we think of when we are picturing the shape of the distribution is we smooth out this shape. You just have 10 or 20 numbers, you have sort of a jagged look. If you would have had 1,000 numbers and you would have had maybe 20 bars, and 20 bars here, you can kind of smooth out the shape a little bit. When this shape is like this, it is called symmetrical. The symmetrical shape, if you picture either histogram or a polygon, means that if you fold it in half, it would be the same on your side. Symmetrical is also sometimes referred to as bell shape. A little bit like a big bell. The thing they really remember is the symmetrical part of it. If you fold it in half, you have the exact same picture on both sides. If you have a picture of a frequency distribution that turns out to be symmetrical, and you found these measures of central tendency, mean would equal the median, would equal the mode. If it is symmetrical or bell shape, the mean, the mode are all the same. So when I look at a group of numbers, I don't have to draw a picture to know what it looks like. If the mean and the median are all the same, it would be symmetrical. Now remember the geographic frequencies of this side. This point right here would be where you had your most frequency. So this number right here would be the node. If the frequencies of the side, this node is the number that appears the most often. Or if it is symmetrical, you fold it over, half pounds on one side of that, half on the other. So that number is not only the mode, it's also the median. Symmetrical, and you have exactly the same on each side. Then this number here, which is the mode, because it's the highest picture is called positively skewed. It's no longer symmetrical, it has been pulled off to one side. That's what skewed is. It's pulled to one side. And positively skewed is in the tail. The longest end is on the right. This is called a right tail. The ends are called the tails, but here the right tail is long. It's positively skewed. And positively skewed means the beam is larger than the beam below. Usually just compare it to the beam. Now I said that the hump is the nose. The beam is larger because of few large numbers. The median should be somewhere in the middle. But if the beam is larger than the median, that is called positively skewed. And it becomes positively skewed because you have a few numbers larger than the rest. You have a few numbers larger than the rest, it becomes positively skewed. This is my picture here. Again, the hump is always the moon because that's the most frequency. If you're rapid frequency outside, the hump is always the moon. Well, this time I have some numbers out here. If the numbers are to the left, that means that they are smaller than the rest. This one is called negatively skewed. Negatively skewed is when you have a left tail. Positive is on the right, negative is on the left. Negatively skewed. This time it means that the average is now smaller. There were a few numbers over here that were smaller than all the rest, and it made your average smaller, but again, the median is always in the middle. Notice always the help. Negatively skewed. A few values or a few numbers were smaller than the rest. Interpret numbers like we have the mean, balance, and the median was 20,000. Now we've already gone through and interpreted those. We said that the average salary was $50,000, the salary that appeared the most often. And then we're also going to look at that when we interpret it, and we're going to say, is it positively skewed, negatively skewed, or symmetrical? And which one do I say if the mean is larger? Positively skewed. The mean is larger. You say, this is going to be something else we're going to add to our interpretation. You say, the numbers, or since they were salaries, you could say the salaries, are positively skewed. Now, when I interpret something, you're not writing an interpretation walk with here on the left. So the columns in the next is here. What would be the average? Sometimes we should pick out the other two. The median is always in the middle. The median is always in the middle. And the mode is always the hump. The mode is the most. So this is the most three. So if you pick out the mode is the hump, the median is in the middle. The mean is the number that's been pulled the most. Or it's been pulled from left to right. The mean is being pulled by this tail. All of the numbers are all the same. We look at the measures of central tendency. And the measures of central tendency we're talking about the mean and the mode. Well, last time we looked at just a long list of numbers. And a long list of numbers is called ungrouped data. There might be sort of groups, there's just a long list of data. We looked at how to find the mean and the ungrouped. Now we're going to look at how to find the mean and the mode for grouped data. Grouped data means that your data is given to you as a frequency distribution. If you have a frequency distribution, how would you go about finding the mean, the median, the mode? The mean for grouped data, is the sum of f times x divided by n. The sum of f times x divided by n. The n we call x bar if we have a sample, and u if you have a population. So if it were a population, it's f times x, we would use a capital N to represent that it was all of the values. But it's the sum of f times x divided by n. We're going to be using this example right here, and I'll give you just a minute to copy these down. These in your student study guide is the frequency distribution we've looked at before, which is the years of teaching experience for a sample of 8 college students, college professors. Years of teaching experience for a sample of 8 college professors. All the way down, and then 4, 9, 14, 19, 29. The frequencies are 16, 21, 12, 11, 10, 8, and 2. Now the frequency tells us that there were 16 professors that had between 0 and 4 years of experience. With the problem we mentioned before, the frequency distribution, we don't know if those 16 professors all had 4 years experience or all had 1 year experience. We don't know. We have lost the exact data. So anytime we're working with a frequency distribution, we will be having an estimate. It'll be just the best guess. We don't have the exact numbers. We don't know exactly what the average will be. So what we upper and lower class limits. 0 plus 4 is 4, divided by 2 is 2. That is the midpoint of this class, because 2 is right in the middle. We do that on down, find the midpoints, 5 and 9 is 14, divided by 2 is 7. Or remember, the class interval is 5. We can just add 5 all the way down to get the midpoint. So we have our midpoint, 2, 7, 12, 17, 22, 27, and 32. Now, because we don't know if those 16 peoples were 0, 1, 2, 3, or 4, we're going to pretend that those 16 people were all around 2. Some of them may have been 3, some of them may have been 4, but those 16 people were all close to 2 years of experience. So we're going to say if we had 16 people with 2 years of experience, we multiply F times X. That's the same thing as writing down the number 2 16 times. So we don't know the exact values, we're going to pretend that that 2 is close enough. That's the reason the formula for the mean says we're going to multiply F times X. Frequency times the mean point. Here F times X is 32. Here the frequency times the midpoint, 21 times 7. 12 times 12. 11 times 17. 10 times 22. 8 times 27. And 2 times 32. Now check the multiplication too. Just a second to check that multiplication. You should always check and double check all of your figures. Are those all right? Then we want to add them up. The total here should be 1,010. Now the formula for finding the mean, and because it's in the sample, do I label it X bar or U? Formula for finding the sample says to take the sum of F times X divided by U. Whenever you see a formula that has this symbol, that summation symbol, you know you're going to have a column that is called F times X and adding that column. Before, when we were doing the mean, we just had the sum of all the X's. So we had a column with all of those numbers and add them up. Well, now we have a column that is labeled F times X, and this number right here is the sum of F times X. So the mean is 1,010 divided by N. But N, this time, has got to be the sum of all of the frequencies. It's got to be the total number of people we're talking about. Well, I can add these numbers up, add up all the frequencies, or how many people were in this group? 80. There were 80 college professors. That means the total right here should be 80. But N is the total of all the frequencies. So we take 1,010 and divide it by 80. I've got 12.625. And I'm just going to keep one decimal place. It's not money, so I don't have to keep 2 decimal places. The general rule, I keep 1 more decimal place than the original numbers. And we know because these class limits were all rounded off to the nearest 1, there was 1 away from here to here, and the original numbers were rounded off to the units. So I keep 1 more decimal place to use. So the average is 12.6. Again, we have to remember that this is an approximate, this is an estimate. We don't know for sure because we no longer know the exact numbers. We were pretending that all 16 people had exactly 2 years. And they might have all had 1 year. We don't know exactly. This is just the best guess we can do if of the next formula was to find the median. And the median, so hold your hand out, the median says n divided by 2 minus CF all divided by f. N divided by 2 minus CF divided by f multiplied times W plus LM. Well, this is one formula that the formula itself usually isn't enough. You usually have to write an explanation of all of these letters to understand what it is. And to find the median, first thing you have to do to find the median is find what is called the median class, or the median group there of the frequency distribution. To find the median class, take n divided by 2. If you had a list of 80 numbers, that would say the 40th number is in the middle. You would take n divided by 2, which means backward working, 80 divided by 2 is 40. Look down the less than cumulative frequency. The cumulative frequency with the arrow pointing down. Look down this column until you find the first value with n divided by 2 or larger. This gives you the median class. You will find in what group the 40th value will be if you look down the cumulative frequency. Then in the formula, CF is the cumulative frequency of the class directly above the median class. F is the frequency of the median class. W is the class width, or I can refer to this as the interval. Class width is the same thing as the interval. And L is the lower boundary of the median class. And you want to emphasize right here is that it's boundary, because common sense to take class limit is the lower boundary of the median class. I can use this band to find a median at this group right here. First step, to find the median class, so to take n divided by 2. So for this group, n divided by 2 is 80 divided by 2 is 40. It says look down the cumulative frequency to find the first group that has 40 or above. We're going to have to find the less than cumulative frequency. That arrow says we add going down the column, go back over here to the frequencies, start with the first frequency, add as we go down, so I'm going to add 21, add 12, add 11, 10, 8, find the median class, because we already said n divided by 2 is 40. You look down this group and you find the first number that is 40 or larger. I say 40 or larger because the number 40 could have been right there. This is called my median class. It's called median class because that is the class or the group that the middle number falls in. You put the numbers in order, the 40th was the middle number, and the 40th number falls somewhere in that group. So that is the median class. Once you've found the median class, we can start filling in the formula, and the formula says first of all, take n divided by 2 minus CF. N divided by 2 minus CF over F times F. What was n divided by 2 for this group? 40. We take 80 divided by 2. The direction said the CF is the cumulative frequency use the median class, so the CF for this one is 37. The class above the median class. So I've got n divided by 2 minus 37 over f. And f, the formula told us, was the frequency of the median class. The frequency of the median class. What is the frequency of this class? Frequency of the median class. Not the class above. The CF is the only one that goes above. Now we're looking at the median class. The frequency of the median class is 11. 12. That is the median class, third class now, and so the frequency is 12. The frequency is 12. The class width should be the same all the way down. What is the class width? Class width is 5. Plus the lower boundary of class. The lower boundary, this is the class limit, this is not boundaries. If you want to find the boundaries, these numbers were all to the ones place. You would have to subtract half of that. You'd have to subtract 0.5 and add 0.5. You don't have to find all the boundaries, you need the lower boundary. Because these were all rounded to here's 1, the difference between here and here is 1. Half of that is 0.5, you subtract 0.5 all the way down here. So 9.5 is the lower boundary of the median class. And like I said, the most common mistake is going to be to take the class limit. So you've got to know this is lower boundary. So the lower boundary here is 9.5. Now when you do this on your calculator, you have to do this one of two ways. Because when you are using a fraction on your calculator, if you punch in 40 minus 37 divided by 12, your calculator divides before it subtracts. So you need to know that anytime you are working a formula that has a plus or minus in the fraction, if you have a formula that has a plus or minus in the fraction, you need to enter in parentheses. Parentheses says to your calculator, do this operation first. Do this first, and then divide by 12. Multiply by 5 and add 9.9. You can do all of this at once on your calculator if you use parentheses. Parentheses 40 minus 37, close the parentheses, divided by 12 times 5 plus 9.5. Now if you're not using the parentheses, you're going to have to go 40 minus 37 equals 3. Minus 37 equals 3, and then take that number divided by 12 times 5 at 9.5. But you can use your parentheses and punch them in all at once. Open a parentheses, 40 minus 37, close a parentheses, divide by 12, multiply times 5, and 9.5. Now because we take one decimal place, when we did the average, I'm going to keep one decimal place. We just want to keep consistent. Keeping one decimal place equal all the way down. Now the last one is the mode. And the handout says that the mode is the midpoint of the class with the most frequency. There's no computation here, you just look at the midpoint of the class with the most frequency. So you look down the class the midpoint of that class, the midpoint is 7. So the mode for this group is 7. Now what you have to remember is that you are picking the group by looking at the frequency. You look at the frequency to find the mode. This is going to be picked. You look at the frequency and you pick the midpoint. Now this may not be the midpoint, but we're saying because there were 21 numbers within this group, most of the numbers were around 7. That may not have been exactly 7, but most of the numbers were around 7. The thing you need to notice here is that the midpoint is not the same as the median class. This is the median class. We found it by looking down the cumulative frequencies, but we found this one by looking down the frequency. Sometimes the median and the mode are the same class. They will not always be the same class. So now that we have the mean and the mode, we always want to interpret it. Average was 12.6, so we say the average years of teaching experience average years of teaching experience for this sample of college professors all of the information that you have. You want to know that it was teaching experience for college professors. You want to know that it's a sample, not a population. If this were an entire college, you would say for the entire college. But get in there, somewhere in your explanation, that it was average years of teaching experience for a sample of college professors. Average years of teaching experience for this sample of college professors was 12.6 years. What was the median? Median was 2.8. We can say half of the professors had less than 10.8 years of experience. Half of the professors had less than 10.8 years of experience. You can also say half had more than 10.8 years of experience. You can say it either way you want to. If you want to emphasize that it didn't have a lot, you say 10.8. If you want to emphasize how old all of these professors were, you say half of them had more than 10.8 years of experience. You can say it either way. And the mode. What was the mode? 7 years of experience of their ensemble. Whenever you find the mean, median, the mode, you should always have these statements interpreted. But the average is half of them or more than the number that are in the ensemble. Then we also look at, is it positive or negatively skewed? To do that, you go back and look at the mean and the median. Don't worry about the mode. If the mean is larger, we write positively skewed. Now, I think to make complete sentences, not always when I say positively skewed, because positively skewed doesn't mean much to most people. Even if I made a complete sentence, this group of data was positively skewed, it doesn't mean much. So we need another sentence, and that's the reason I don't always make this a complete sentence, because the next one is what really explains it. It's positively skewed, a few numbers were larger than the rest. teaching experience than the rest. And a few mountains were larger than the rest. Yes, Strayman's reputation we did was he had a list of numbers. The list of numbers was called an root. They're interpreting it exactly the same when we have a root. At Chapter 3, Section 3. Chapter 3, Section 3 is called Measures of Variation. Last section we looked at what was called measures of central tendency. The measures of central tendency were the mean, the median, the mode. They told you what was going on around the middle of the numbers. The median was the middle, and because the mean averaged all the numbers, it was sort of in the middle. But now the variations are going to tell us what's going to happen if the numbers aren't right close to those middle numbers. Variation is going to tell us, are the numbers spread apart, or are all of the numbers very close together? They're telling you how the numbers vary. The first measure of variation we're going to look at is the simplest measure, and it's called the range. The range for any set of numbers is simply the highest number minus the lowest. The difference between the high and the low tells you if there's a lot of difference between the numbers or if they're close together. A small range would tell you all of the numbers are real close. A large range tells you that the numbers are spread apart fairly far. That's the simplest and the easiest, but it doesn't quite tell us as much. So the other measures of variation we're going to look at are the variance and the standard deviation. The variance and the standard deviation, again, are a measure of how much the data is varying. They tell you if all the numbers are close together or if all the numbers are spread apart. The variance is labeled with this letter right here, which is called a sigma. We've already looked at a capital sigma, which means the summation, the sum symbol, but this is the lowercase sigma. Just like in our alphabet, we have capital letters and little letters. In the Greek, they have capital letters. This is a capital sigma. This is a small sigma. The small sigma, sigma squared, is the variance. We put a square on it. Sigma squared is the variance of a population. If you remember when we looked at the mean, we had two different designations for the mean. We called mu was the mean if we had a population, but x bar was the mean if we had a sample. And it was just a way of labeling it so that we knew if you were working with all of the data or part of the data. Again, we have a different label if we are working with a population or a sample. The population is sigma squared. It's f squared if we are working with a sample. So we have to make sure we know whether we're working with all of the data or just part of the data so we know how to label it. Sigma for a population, f for a sample. The standard deviation, then, we take the square off. The standard deviation is sigma for a population and just f for a sample. When we work our formula, we usually find the variance. We'll take that number, and if you take the square root of it, then you will have the standard deviation. In the mean, it didn't make any difference how you found the mean, whether it was a population or a sample. But in the standard deviation, there is a different formula for the population than there is for a sample. So it's very, very important that we know the difference, whether we're working with a population or whether we're working with a sample. The first formula I'm going to look at is the formula for the variance of a population. Remember, variance is sigma squared. Once you take the square off, that's the standard deviation. The variance for a population is the sum of each x minus the mean squared and divide that number by n. This says to take each and every value, this is your each x, subtract the mean, and then subtract that, square that difference. Each x minus the mean, square the difference. Add up all of those and divide by n. And this is the variance. To get the standard deviation, we simply take that number, whatever number you got there, and take the square root of it. When you have sigma squared, if you simply put a square root, you get sigma, and that will give you the standard deviation. When we're working with these, we usually go ahead and find both numbers. You go ahead and find the variance, write it down, take the square root, and that's the standard deviation. But it's the standard deviation we will use the most, it's the standard deviation we will interpret. The standard deviation is used the most because this is the value squared. If it was something measured in money, this would be dollars squared. Once you take the square root, it's back to being dollars again. So we don't interpret variance because it is something squared. But the standard deviation is the same unit of measurement as the regular numbers. If the regular numbers were years in age in years, these would be years. So the standard deviation is the same unit of measurement as the original numbers, but the variance is that unit squared. That's the reason the standard deviation is used the most often. Now this is a formula that we first look at when we're studying variance and standard deviation because it's telling you what you have. You're taking each individual value and seeing how far that is away from the mean. And that's exactly what the variance and the standard deviation tell you. Are the numbers close to the mean? If you have a small standard deviation, then all of the numbers are close to the mean. But a large standard deviation says the numbers are not close to the mean. There's a lot of variance in your numbers. But this formula is not the formula we actually use. The reason we don't use that is because sometimes it's hard to take each number minus the mean. If the mean didn't turn out to be a nice even number, if the mean was something like 2.835, and you subtracted it and then squared it, you'd have a lot of computations. So this is the formula we look at first, just so that you can see what standard deviation is. Standard deviation measures how far each number is away from the mean. But we use a slightly different formula for computation because it's an easier one to use. And the formula we're actually going to use for computation says the variance is the sum of x squared minus the sum of all of the x's in parentheses squared divided by n, all of this divided by n. Remember, n is the total number of values, just like it was in the mean. How many numbers did you have listed? That's what n is. And we use a capital N because this is a population. This is all of the numbers. Again, this formula right here is for population because we call it sigma. And this formula is easier to compute if you know how to handle these summation signs. This says add up all of the x squared. Because the squared is on the x, you square each number and then add it up. But this in parentheses said that you added up all of the numbers and then you square that total. You have to be careful with what those parentheses are telling you. This says you're adding them all up and then squaring that total number. Divide it by n, divide all of it by n. So of course if that's the variance, the standard deviation is simply the square root of this amount. The variance has a squared on it. Once you take the square root, this is now standard deviation. And this is what you would use if you knew it was a population. But if it's not a population, if it's a sample, we have a completely different formula. The computation formula if we have a sample. It's called S squared instead of sigma. So the label is telling us what we're working with. We're working with a sample. S squared, again, is the sum of all of the x's squared minus the sum of the x's, then square that total divided by n minus 1. Now the little n is just telling us it's a sample. Capital N was a population, that was all of the people. Little n is a sample. The difference between this formula and the population is you're dividing by n minus 1. So the standard deviation S is simply the square root of this amount. Sum of x squared minus the sum of x in parentheses squared over n minus 1, take the square root. This is the formula we will be using the most often because you have a sample more often than you have a population. It's easier to take just a part than it is to take all of the total numbers. So now I am going to find the variance and the standard deviation for a sample of numbers. These sample of numbers I'm going to put up here are the cost of a speeding ticket. And if we took a sample of tickets, you always have to be told whether it's the population of the sample, because you don't know if this is all of the numbers. Maybe this is all of the numbers from one particular day. Then it would be a population. But if it's a sample of all the tickets given in a year, then you have to know that it's sample with the formula is going to be slightly different. If this is a sample for the cost of speeding tickets, and the numbers are 25, 30, 65, 70, 40, 55, 60, 35, 50. If these are all of the speeding tickets given in my sample, and this is the cost. It doesn't say you were going 25 miles an hour. It says your cost, you had to pay $25. It's important to know what these are labeled, because the label on the standard deviation is going to be the same thing. If these are dollars, my standard deviation is going to be dollars. So now I'm going to look back at the formula and see what the formula tells me to do. The formula for standard deviation says the sum of x squared. Whenever you see this symbol right here, you know you're going to make a column and add up everything that it says after it. So it says to take x squared and add them all up. The original numbers are always labeled our x's. They're our variables. So we're going to need another column over here that says x squared. And we are going to square each one of those numbers. So I'm just going to take 25 squared and write that down. Okay, now you might want to get your calculator and work along with me so that you can see where I'm getting these numbers, but we're just going to continue squaring each one of these numbers. 30 squared, 65 squared, 70 squared, 40 squared, 55 squared, 60 squared, 35 squared, and 50 squared. And now we're going to total up this column with the total of the x squareds. So now we just have to add all these numbers up. 625 plus 900 plus 4,225. We're just going to add all of these numbers up. I get 22,600. Now at this point you always want to stop and double check, because you have a calculator. There is really no excuse for making a mistake error. So always at least check it twice. You might want to triple check it, but always make sure that these numbers are added up. So real quickly I'm just going to add the numbers up again. to make sure I did not have a mistake. And I got the same total again, so probably I didn't make a mistake. Now the formula said first the sum of x squared, then it said minus, in parentheses, the sum of the x. So we're also going to have to add up this column. We're going to have to add up the x column. 25 plus 30 plus 65. Just total this column also. And again, you always want to check to make sure that you haven't made a mistake. It's so easy to make a mistake, and it's so easy to check it here on the calculator. Let me try it again. I didn't get that number again. Okay. So it is 430. But you always want to check and double check to make sure that you have these totals correct. Now that I have these totals correct, I'm ready to go over here to the formula, and I'm looking for, first I'm going to find the variance. The formula for the variance said the sum of the x squared. So I look at this column right here, the x squared column, 22,600. I'm going to subtract. Now the formula says take the sum of the x's and square that number. So I'm going to look at the sum of the x's, which is 430, and I'm going to write 430 squared. All of that is divided by n, and n is the number of values. So I just come over here and count. I have 9 values. Now all of that is divided by n minus 1, so that's all divided by 8. Now this formula, what I have to remember when I go to my calculator is how to punch it in. We have to remember that in order of operations, you would do everything on top of the numerator before you would divide. If you punch it in exactly like you see it, 22,000 minus 430 squared divided by 9 divided by 8, it's going to divide by 9, and then it's going to divide by 8. Well, you want all of this totaled up before you divide by 8. So you need to get used to any time you have a fraction in a formula. If you have anything added or subtracted on the top, you need to put that in a parentheses. When you enter it, you're going to first enter the open parentheses on your calculator, 22600 minus 430, the x squared button, divided by 9, close the parentheses. You do everything in the numerator first. We do everything in the numerator, close the parentheses, then divide by 8, and then hit your equal. If you don't put the parentheses in, you will not be getting the correct answer on your calculator. So I'm going to hit parentheses, 22,600 minus 430 squared, divided by 9, close the parentheses, divided by 8. So my variance is 256.9444. Now, when you're going to write down the variance, don't get rid of it here on the calculator because we're not through with this. Write it down. You can round it off to 2 or 3 decimal places. If we're talking about money, you might round it to 2 decimal places. But leave all of the numbers here. Do not round off the variance and then use that rounded answer to find the standard deviation. I want to use these complete numbers. Now to find the standard deviation, I want the square root of that number right there. So to find the standard deviation, I've left that number on my calculator. All I have to do is say take the square root of that number, and I get 16.029487. Now again, remember that this is talking about money. If it's talking about money, we always round it to 2 decimal places. You don't say $16.0. You don't say $16.029. In money, it's always 2 decimal places. If it was not money, the general rule is to keep 1 more decimal place than the original numbers. all of these original numbers did not have a decimal place, and you would just keep one decimal, except in money. Money is always exactly 2 decimal places. Now, we have the variance and we have the standard deviation. We've mentioned before that we always interpret. Just finding these numbers is not enough. We always interpret these values. But you don't usually interpret the variance, because on the variance, all of these numbers have been squared. That's 256 square dollars. It doesn't make any sense. But because you've now taken the square root, this is now $16. We can interpret the standard deviation. And after we find it, the next step is to always interpret it. The standard deviation is $16.03. We say the numbers are an average of $16.03 away from the mean. Because that's what the standard deviation is telling us. It is telling us how far the numbers are away from the mean. So here the numbers are an average of $16.03 away from the mean. But the next thing we always do is we always try to say, is this a large deviation or is this a small deviation? And we can't tell by looking at it whether 16 is a large deviation or not. We cannot finish our interpretation of deviation unless we know what the mean is. We were working with a sample here, so the mean would be labeled X bar. And remember from last section that the mean is the sum of all of the x's divided by n. The mean is just the average number. We want to take the sum of the x's and divide it by n. The sum of the x's was 430. I want to take that number and divide by n. N is 9 because we have 9 numbers. So the average is 47, and I'm going to round it to 2 decimal places, $47.78. So the average cost of a speeding ticket was $47. Now, if the average cost is $47, and the numbers are an average of 16 away from that cost, 16 away from 47 is a large difference. So let's say that this was a fairly large deviation. A fairly large deviation means the numbers are not close together, or you might say that they're not real close together. There's no absolute here, that this is close, this is not close. These are not real close together. Oh, the numbers are not real close together. If it's a large deviation, the numbers are not close together. And this is one more fact that we know about this set of numbers. When we learned about the mean, the median, the mode, we were describing a set of numbers. Well, this is one more way to describe the numbers. If you just had the mean, the median, the mode, and the standard deviation, and you looked at those numbers, you should be able to tell a lot about what's going on without actually looking at the real numbers. Now here we had 9 numbers, it's not hard to look at them. But if you had a list of 50 numbers, this summarizes the numbers for you real quick. But the standard deviation just told you what was, the mean, the median, the mode just told you what was in the middle. Now we know if all the numbers are close together or not. We interpret standard deviation, we do not interpret variance. Now, the problem usually is deciding if that is a large deviation or not. We can't always say 5 is large, 10 is extra large. You can't say that. These are a comparison to the mean. If I have a mean of 210 and a standard deviation of 8. If your average is 210, 8 is not very far away from 210. So this would be a very small deviation. if it's a small deviation, the numbers are close together. Very small deviation, the numbers are close together. But if I had a mean of 15 and a standard deviation of 8, if your average is 15 and the numbers are 8 away from it, that is a large deviation from 15. So the same standard deviation 8 is small when you compare it to 210, but it's large if you compare it to 15. So this would be a large deviation. Numbers are not close together. So standard deviation cannot be interpreted until you compare it to the mean. Is it far away from that number? Sometimes it's a little difficult to decide. Well, is this very far away from that number? This example here was fairly easy to see that 8 is pretty far away from 15, but 8 is not very far from 210. But sometimes it's not quite as easy to see, is it small or is it large? So we use another value to help us tell if it's a large deviation or not. And that value is called the coefficient of variation. The coefficient of variation is used to make it easier to decide if it is a large deviation or not. Coefficient of variation is abbreviated capital C, capital D, and it is the mean, it is the standard deviation divided by the mean, and you make it a percent. To make it a percent, you either multiply by 100, or you can make it a percent by just moving your decimal and putting a percent sign. But it's the standard deviation divided by the mean. If it is a population, it's the standard deviation divided by the mean. It's the same formula, it's just labeled different. This is standard deviation of a sample, standard deviation of a population. And coefficient of variation makes it easier to see if you have a large variation or not. There is no exact rule here, but once you change it to a percent, it's easier to see how much variation there is. And anything from 0 to 20% is usually considered pretty small. Pretty small variation, the numbers are close together. So you can see that a coefficient variation of 5, you would say this is very small deviation. But as we start getting up from 20, maybe to 30, somewhere in that region, that's getting to be some. It's a little, it's still not too big, but that's some deviation. Again, there is not an exact wording here. You don't cut it off exactly at 30 and exactly 31, but anything around 30 is some deviation. The numbers are not real close together. But you start getting over 30, and especially as you start getting around in the 40s and the 50s, this is getting to be a large deviation. So by the time you get to 50%, that is a very large deviation. And anything over 50 would be very, very large deviation. And you're not going to find this printed in a book anywhere because this is not an exact rule. This just sort of gives you a general rule of thumb to think about. If it's 20%, that's small deviation. But if it's 58%, that's very large deviation. Very large deviation. Like I said, this is just sort of a rule of thumb to help you tell if you have a large variation or not. Coefficient of variation is also used if you need to compare two different standard deviations to see which is varying the most. If you have a company and you make bolts, and you measure the weight of the bolts, and the average weight of the bolt for this sample, you one day went in and picked out a sample and you took the average weight, and the average weight turned out to be 25 millimeters with a standard deviation of 7. And the standard deviation is the same thing as the mean. If they're millimeters, this is millimeters. But then you not only weighed each individual bolt, you looked at the diameter of the boat. Now wait a minute. You can't weigh in millimeters. Let's make it milligrams. Sorry. A weight has to be milligrams. But then you go measure the diameter of the boat. And when you measure the diameter, maybe the mean is 8 millimeters with a standard deviation of 3 millimeters. Okay, are we out? So if I were to compare the weight to the diameter and see which one was varying more, is the weight varying more or the diameter varying more? I cannot compare milligrams to millimeters. It looks like 7 is a larger variation in millimeters, but you cannot compare milligrams and millimeters. But if you find the coefficient of variation, you've changed it to a percent, and you can compare 2%. The coefficient of variation for the weight would be 7 divided by 25. The coefficient of variation for the diameter would be 3 divided by 8. Now the formula said to multiply by 100, but I'm just going to move the decimal over. 7 divided by 25 is 0.28. I'm going to move that decimal over and say 28%. 3 divided by 8 is 0.375. I'm going to move it over and say 37.5%. Well, you can see that this one had some deviation. They were not real close together, but this one had more deviation. So the diameter is deviating more. Diameter is deviating more than the weight. So once you changed it to a coefficient of variation, you can now compare percents and see which one is varying more. And in manufacturing, this would probably be important because the diameter determines whether your bolt is going to fit or not. And if the diameter is varying, then you're not going to have a good product. So you need to check how much each one of your product is deviating. And here a large deviation says you need to check and see what's happening in your process. Okay. We're now going to look at two different applications of the standard deviation, besides just telling how much your numbers are varying from the mean. Two of the formulas that use the standard deviation to tell you some more about the data. The first one is called Chebyshev's theorem. Chebyshev's theorem says, and this is written in your handout so you don't have to copy it if you don't want to, but Chebyshev's theorem says for any set of data, that means it can be positively skewed, negatively skewed, for any set of data, at least 1 minus 1 divided by k squared of the values will fall between the mean plus and minus k times the standard deviations, where k is any number greater than 1. This means you can pick a value k. You can pick k to be 1.5 or you can pick k to be 3. You can pick any value for k, take 1 minus 1 over k squared. That's going to give you some sort of fraction. Maybe it's going to be 3/4 or maybe it's going to be 2/3. But it's going to say at least 2/3 of the values fall between the mean. If you multiply k times the standard deviation and add it to the mean and subtract it to the mean, you'll get a range. And at least this fraction of the values are between these two numbers. Chebyshev's, like I said, is used for any set of data, whether they're negative or positively skewed. The empirical rule, though, is another rule, but it's only for symmetrical distributions. Remember, symmetrical distributions were also called normal, and that means that the mean and the median and the mode were all equal. anytime you want to use the empirical, they have to tell you that it was symmetrical, or sometimes they will use the word normal. Normal means that it was symmetrical. So if we know the data is symmetrical, we can use the empirical rule that says at least 68% of the values fall between the mean plus or minus 1 standard deviation. You're not allowed to pick K. It's always 1 standard deviation. This is just a flat statement. 68% of the values fall between the mean plus and minus 1 standard deviation. At least 95% of the values fall between the mean plus and minus 2 times the standard deviation. And at least 99.7% of the values fall between the mean plus or minus 3 times the standard deviation. Chebyshev theorem, you can use a little bit more leeway. You can pick any K that you want to, but empirical just has it for 1 standard deviation, 2 standard deviation, and 3 standard deviations. The empirical rule again applies if it was normal, and we said if it was normal, it was symmetrical. When you drew a picture of the graph, you had a bell-shaped curve here, and the bell-shaped curve, if you folded it in half, was exactly the same on both sides. If this was a normal distribution, then this number here in the middle was the mean, it was also the median, it was also the mode. If it was symmetrical, this represented all 3 of those values. And what the empirical rule says, if you come out here and take the mean and add 1 standard deviation, and you take the mean and subtract 1 standard deviation, 68% of the values are going to be between these 2 numbers. And you can see on your graph that that's a big chunk of your graph. That's a large percentage of your graph. 68% of the graph is going to be between these 2 values. When you're looking at shapes, there can be different shapes even if they are symmetrical. Now both of these pictures were symmetrical, but this one was much closer together. This number here is still the mean, the median, and the mode. But this time, if I'm 1 standard deviation away, and 1 standard deviation away this way, still I would get 68% of the values, but you wouldn't have to go as far to get 68% of the values. So that says the standard deviation would be smaller. This picture right here does not vary as much as this picture because they are all closer together. The standard deviation is smaller, so this range is smaller. On this picture, the numbers are not as close together. The standard deviation would be larger, and this range would be larger. But it's still 1 standard deviation has 68% of the values. But you can only use the empirical if you know it is normal or symmetrical. I'm going to work some examples of Chebyshev's and of the empirical rule. These examples are in your student study guide, page 47. These examples are also written in your handout if you want to look in your handout. On the handout, the first one I'm going to look at is called example 17. It's example 17 in your student study guide, or it's in your handout. This problem says, for a data set with a mean of 212 and a standard deviation of 18, what percent of the values will fall between 185 and 239? This did not tell you it was normal. If it was not expressly told that it's normal, then you'll have to use Chebyshev's because you do not know if this is a normal distribution or not. So if they don't come right out and say normal, you have to use Chebyshev's. They told you the mean is 212 and the standard deviation is 18. They want to know what percent of the values are between 185 and 239. When you are given the range, what you then have to do is find out how far each one of these numbers is away from the mean. When you have a range, that means been added to the mean, that same number has been subtracted from the mean. And if you look right here, 212, 27 has been added over here, and 27 has been subtracted over here. But both of these numbers should be the same distance away from the mean. They are both 27 away. So if we now know that the number that's been added was 27, Chebyshev tells us that the mean plus k standard deviations is how far away you go from the mean. So if you went 27 away, the mean plus k standard deviations was 239. This was the range. Chebyshev says the range is the mean plus k standard deviations, or the mean minus k standard deviations. If I know that the mean is 212, and I know the standard deviation is 18, I can now solve for k. If I subtract 212 from both sides, it was 27 away, which is what we said when we looked at the range. Now to solve for k, I'm going to divide by 18. And 9 will go over there 3 halves. You can leave it 3 halves or go 1.5. So k is 1.5. This time you didn't know k, you had to solve for k by knowing that the mean added ks gave you the upper range. You could have also used the equation, the mean minus k times s, with the lower value 185. You should have gotten the same value of k whichever way you solved it. Now that we know k, they want to know what percentage. So we're going to take 1 minus 1 over k squared. And we're just going to go to our calculator and go 1 minus 1 divided by 1.5 squared, hit an equal. But we're going to change this to a percent, and we're either going to leave it 56 or 55.6%. Now again, when we solve for something, we don't ever quit at this point. We always write a statement about it. And this statement says at least 56% of the values fall between 185 and whatever that number is, 239. We don't just say 56% will quit. We never stop without interpreting it. At least 56% of the values fall between 185 and 239. The next example I want to look at is still in the student study guide, or it's in your handout. It's labeled Example 18. Example 18 is going to give us different parts of values, and we may have to solve for a different letter than k. Any piece they give us, we can solve for the missing piece. Example 18 says 80% of the values fall between what two numbers? If the mean is 105 and the standard deviation is 12. 80% fall between what two numbers? Again, we have to use Chebyshev's. We cannot use the empirical because it does not say that it's normal or symmetrical. If I know 80%, 1 minus 1 over k squared has got to be 0.8. Instead of 80%, I work with 0.8. I need to solve this for k squared. So I'm going to solve it just like I would in algebra. The first thing I do is subtract 1 from both sides. So 1 minus k squared equals to a negative 0.2. You need to take your calculator and go 0.8 minus 1. Now, if I multiply both sides times a negative, I would just get 1 over k squared equals 0.2. Just to get rid of the negative, multiply both sides times -1. But now what I want to do anytime I have a fraction is multiply by that denominator to eliminate that denominator. Here when I cancel, I get 1 equals 0.2k squared. That's just what you learned in algebra. To eliminate a fraction, you multiply both sides times the denominator. To solve for k squared, I get 1 over 0.2 is k squared. Then all I have to do is take the square root. The square root of 1 divided by 0.2 equals k. On your calculator, make sure you go 1 divided by 0.2 and hit an equal. 1 divided by 0.2 is 5. Then take the square root of that number. So I get 2.23 is k. Now, I still need to read the problem and see if I answered the question. The question says 80% of the values fall between what two numbers? Well, this didn't answer the question. I just solved for k. But we know that the mean plus or minus k times the standard deviation will give us at least 80% of the values. The mean this time was 105. The k is 2.23. Standard deviation is 12. So I can take 105, subtract 2.23 times 12, and get 78.24. But then I also have to take 105 and add 2.23 times 12 and get 131.76. Again, we write a sentence to explain this. This is not our final answer. We write a sentence to explain what we've got, and we say at least 80% of the values fall between 78.24 and 131.76. At least 80% of the values will fall between 78.24 and 131.76. Yeah. The next example I want to look at is example 19 in the student study guide. Again, this is also in your handout and it's labeled example 19. Example 19 says if a normally distributed group of numbers. But example 19 told you it was normal. If it tells you it's normal, we don't use Chebyshev's, we use the empirical rule. In a normally distributed group of numbers, 95% will fall between what two values if the mean is 18 and the standard deviation is 5. 95%, according to the empirical rule, is 2 times the standard deviation. Just refer back on your handout to where you see the empirical rule, and it says at least 95% are the mean plus and minus 2 standard deviations. And because they told us 95%, we know we're going to take the mean plus or minus 2 times the standard deviation. Well, the formula here said X bar and S because this formula refers to a sample, but the same formula works for mu and sigma. It would just be mu plus or minus 2 times sigma. So the formula is the same whether you have a sample or a population. X bar or mu are both the mean.
I mean, I
So here
can
we're
listen,
taking
but
18 plus or
sorry,
minus
are you
2
there?
times the standard deviation. 18 minus 10 is 8. 18 plus 10 is 28.
Thank you.
So what we say here is at least 95% of the values fall between 8 and 28. The thing to notice here was we could use the empirical because they told us normal. If they didn't tell us normal, we would have had to use Chebyshev's. we're going to look at the measures of variation for grouped data. And grouped data was when you had your numbers in a frequency distribution. If you have a frequency distribution and you no longer have the original numbers, you can still find, we looked at last time, the mean, the median, the mode. Or you can also find the standard deviation. The standard deviation for grouped data here, I'm just going to give you the one for the sample, S. S is the sum of f times x squared minus the sum of fx squared divided by n, all of it divided by n minus 1, and take the square root. Now again, the variance is that number before you took the square root. So s squared would be all of this before you take the square root, and that would be the variance. The only difference, if you did have a population, this is for the sample is S, the sample divides by n minus 1. If you did have a population, it would be sigma, and you would divide by n on the bottom. The only difference between the sample and the population. Sample you divide by n minus 1 on the bottom, population you would divide by n if it were a sigma. So this formula, again, these summations are telling us what to do. This says we have to have a column that is f times x squared. Well, on grouped data, f was the frequencies, how many were in each group, and x was the midpoint. So we have to multiply the frequency times the midpoint squared. Here we multiply the frequency times the midpoint. Here we add all of those up and then square the total. This says we square each x, multiply it times f, and add it up. But this says you add it up first, and then you square that total, divided by n minus 1. So I'm going to look at the same set of data that we looked at yesterday and found the mean. This is years of teaching experience for the college professors. Number of years of teaching experience for a sample of 80 college professors. That meant that 10 of these college professors had between 20 and 24 years of teaching experience. This was a sample of 80 college professors. What we have to know is we have to know the midpoints. So the first thing I have to do to find the midpoints is just make a column labeled x. Midpoints are always labeled x. And the midpoint you take 0 plus 4 divided by 2 is 2. The next one you take 5 plus 9 is 14 divided by 2. Or you can say if the interval is 5, you can add 5 to get the rest of the midpoints. So we have our frequencies, we have our x. We next need a column that is f times x. We need to multiply each one of those frequencies times its midpoint. And add this up. Again, I'll use y'all to double check my figures to make sure I've got it right. You should always double or triple check this if you're doing it on the test. Now we need another column here that was f times x squared. Because the formula said we needed f times x squared. This is the fx column. I'll square that total, but this one says f times x squared. Now what we've got to remember for the f times x squared column is that the squared is on the x. We can't square this number right here. If I squared the 32, I am squaring the x and the x. This just needs to square the x. So you square the x and get a 4, multiply it times 16. You do not square this column because that's going to be squaring the f also. You square this and get a 4 times 16. Now another way to do the fx squared column is to remember that you already have f times x. Take the fx column and just multiply times 1 more x. You already had f times 1x. This is f times 1x, multiply it times x again. So the next one, I'm going to take 147 times 7. Fx column times another x. 144 times 12. 187 times 17. And add all of these numbers up. Y'all agree with me there on the column? Okay. Now that we know these totals, we know the fx column, and we know the fx squared, and also we need to remember that n is 80. N is the total number of frequencies. You don't come over here and count 1, 2, 3, 4, 5, 6, 7 groups. We're not counting the groups. N is the total number of frequencies here. So now when I go to my formula that says the standard deviation is the f times x squared. I look at my column here, and the f times x squared is 18720. That's this first number. Sum of fx squared is the fx squared column. Then the formula says minus the fx column squared divided by n. The fx column minus the fx column squared divided by n, and everything divided by n minus 1. If you write it down first, that's going to be the variance. If you then take the square root, you'll have the standard deviation. Again, you have to remember to put that parentheses around the top. You have to put a parentheses here. Minus 110 squared divided by 180, close the parentheses, divide by 79, and hit an equal. Now this first number you get is the variance not what I got. That's what I got that first time. Try it again. Okay, let's try that one. So I got 75 for the variance. But we're going to take the square root of that number for the standard deviation. So the standard deviation is 8.7. formula, you're punching in those parentheses, 18720 minus 110 squared divided by 80, close parentheses, divide by 79, then hit an equal. So the standard deviation is 8.7. The standard deviation is the same unit of measurement as the original years. These years were, this is the number of college professors, this was their years of teaching experience. So this 8.7 is 8.7 years of teaching experience. It's the same unit of measurement as whatever the original numbers were. Now, to interpret the standard deviation of 8.7, you cannot interpret the standard deviation unless you know what the mean is. And we said the mean is the sum of fx divided by n. We found this last time, fx. Fx this time was 1010 divided by n. You cannot interpret standard deviation unless you have a mean to compare it to. The mean is 12.6. Now the interpretation of the standard deviation. The numbers are an average of 8.7 years away from the mean. This statement is always exactly the same. You just fill in the blank here of the number. The numbers are an average of 8.7 years away from the mean. If my standard deviation is 8.7 and my mean is 12, is this a large deviation? It's very large because 8 is a long way away from 12. Now, when in doubt, if you don't know if 8.7 is large or not, always find the coefficient of variation. Take the standard deviation divided by the mean, 8.7 divided by 12.6. If you have any doubt at all saying, well, that's a large number or that's a small number, you find the coefficient of variation. And the coefficient of variation this time is 69%. So yes, that's a very large deviation. So you would say, this is a very large deviation. The numbers are not close together. Now, if I don't ask for the CV, a lot of times you want to go ahead and find it to make your interpretation a little bit easier. I didn't particularly ask for it this time, but sometimes you want to help it. You want to use the coefficient of variation to help you decide if that's a large deviation or not. The very large deviation, the numbers are not close together. Like I said, last time we looked at the central tendency, the mean, the median, the mode. They told you what happened in the middle. They told you the average. But now you're going to see if the numbers are close to the average or not. And that's just one more piece of information about the data. Remember, this is all summarizing the data, so that you don't have to look at all the list of numbers. If you know the average, and you know if the numbers are close to that average or not, you get a good picture of what is happening with that set of data. Okay, any questions here? It's just another formula we have to use if it's grouped data.